All right, example 2. I thought this was going to be in the last video, but that got interrupted by a phone call, which it is what it is. It's insurance. So in the last example, we could by sight. This is kind of like what I call like lovely made up data that is perfect. Okay, but in the next one, we see some caffeine again. No. In one of them, it was, oh yeah, the textbook uses caffeine. I had an ibuprofen one. Anyway, whatever you take it in and burn it out. So you've taken some caffeine and it's in your bloodstream, and then your body is metabolizing it. And so it's not perfect data. My guess is that the ratio between each level is not perfectly the same. So if I say 72.3, oopsie. So it says, by the way, use your calculator to create an exponential model. So I didn't even think, is this going to be linear or not? It just immediately told me, in case you're wondering, because normally I'd be like, whoa, what is the pattern? So 72.3 divided by 8 is that. 63.2 divided, did I just do by 80? Yeah, 80. By 72.3, 0.87. So notice how these are all a little bit different. They're close to each other. So all of these ratios are close to each other, but the question is, what do I choose? Yeah. And so enter in the regression, because it's going to find the best number to choose for the pattern, so that we get the closest and least amount of error. So use your calculator to create an exponential model for this data. All right, let's do that. We're going to go stat. And what we're going to do is, I already have data in here, so I'm going to clear it. We're going to put the hours into list 1. 0, 1, 2, 4, 5, 6. Got it. And the data that is given for list 2, 80, 72.3, 63.2, 55.7, 51.8, 42.4, 40.9. Got it. And making sure that they line up because they correspond to each other. That's immediately after 1 hour. Now there's 72.3 grams, or I'm sorry, is it milligrams? Milligrams in the bloodstream, etc. So we want to make sure they really line up so that that correspondence is obvious and doesn't get mixed up at all. Otherwise, it'll give us the wrong model. So now let's figure out how the calculator would give us that model. Stat, it's very similar to when you made a linear regression. Stat, calculate, and now it's not the statistics for the mean, median, or the mean, the median, the quartiles, the standard deviations, and whatnot. It is, let's see, it's not a linear, it's not a quadratic, a cubic, a quartic, linear, it's not a, where is there it is, exponential regression. So I hit enter. Okay, our independent variable is L1, the time. Our dependent variable was caffeine, it's in list 2. I hit enter many times, and I get this. Oh my goodness. Hold on, it doesn't have the diagnostics on it, so I'm going to actually turn it on right here. So in case you're thinking, what are you doing, lady? I went to mode in order to find the regression. So I'm going to do it actually again. Go down to exponential regression, list 1, list 2, hit enter many times. Okay. The only thing I just turned on is this. And if you don't have that on your calculator, you can turn it on. So clearly indicate, so use your calculator to create an exponential model. Here we go. The Y in our case is caffeine. So I'm going to write C for caffeine is equal to A. A is approximately 80.2 times B is approximately 0.889 or 0.89. Okay, to the maybe hours, to how many hours have passed. Okay, So there is our exponential model. Or this is the initial, that's close. It's not perfectly the initial amount. And this wasn't perfectly the ratio between all, but it's the best fit, hence the name regression. So regression means let's regress to just acknowledging we're just having the best possible one with the least amount of error, but it will still have some error. It's just the best possible outcome. So let's see, C equals milligrams of caffeine in bloodstream. And H equals hours after intake, consumption, or whatever. What does the A represent? Well, in this, remember, A is that 80.2. The A is the initial. So A equals 80.2 here. Initially, the person took, 80.2 milligrams of caffeine, or ingested, like you ate it, you drank it, whatever. Initially, the person took 80.2 milligrams of caffeine. Even though it says 80, it's not perfect, it's all right. What does B represent? So in the B, right? B for base. The B is the 0.89. It's an approximation. So let's change that to an approximation. And that means that this, okay, we'll keep those as equals, but really we would be computing approximations. What does it represent in this situation? Well, here's the thing about that. What it really means is each hour, okay, oof, I have ideas here, so I'm going to have to write a little smaller. Each hour has 89% of the caffeine left from the previous hour. Okay, so each hour that passes, you only have 89% of what was before. That means there's a certain amount being, eliminated or metabolized. And how much is the difference between that and 100%? 11%. So I would say this also could imply 11% of the caffeine is being metabolized each hour that passes. Or eliminated by the body. Okay, use your graphing calculator to make a scatter plot of the data along with your model. So this, by the way, this is the model equation, aka best fit, aka regression model. Okay, just so that, yeah. All right, let's do it. Back to my calculator. I'm gonna say second stat plot. Okay, I'm gonna hit enter for number 1, and I'm gonna turn it on. So I'm gonna hit enter. I'm gonna go down to this one with all the dots. So I want it to be a scatter plot. The X's were list 1, and remember that is off of here. So I'm gonna go second 1 to turn that into list one. And my Y's, which was the caffeine, so this was hours and that is caffeine, is stored in list two in the statistics. Okay, so now that'll have the scatter plot. So just zoom going down to statistics like we did when we were doing linear regression. I see that. Okay, so there's my scatter plot, but it also says with the model. So I'm going to go to y equals, and this highlighted means that the scatter plot is on. And we said it was 80.2 times 0.89 raised to the hours, or I'm going to call that x in this case. Okay, and now I'm going to go back to graph. And we're going to see how well it actually did at matching up with that. It did pretty good. I mean, it did a pretty good job, I would say. It's not perfect, right? So that one's a little under, that one's a little over, but it found a happy compromise between everything, the best compromise, as a matter of fact. Hence the name, best fit for the regression model. Okay, so sketch it here, it says. Okay, the title with this would be caffeine in bloodstream. This would be labeled with milligrams. This would be labeled with hours after intake. Okay, and then it says make a sketch on it. Okay, so I'm going to keep this here for visualization. Oof, there's a shiny glare there. I see something like that, and then a little bit of this, and a little bit of that, and a little bit of this, and a little bit of, Yep, got it. And the model did something like that. Okay. It's nice. Predict how much of the caffeine will be left in the person's bloodstream after 14 hours. Okay, well, now I want to go back up here and say this is hours after intake. So we are given H equals 14, and it asks for the amount of caffeine. So C equals question mark, H equals 14. Well, here's our model. Okay, so caffeine is approximately 80.2 times 0.89 to the 14th power. There we go. On. I go second quit to get back to main screen. 80.2 times 0.89 to the 14th power. About 15.7. About 15.7 milligrams. It's just slowly leaving the body. Okay, and now we see this thing called half-life. Half-life. So let me tell you what that means. Oh, and just to, have a good reference here, but this was the explanatory variable, aka x's. I said this out loud, but I do like to write it. This was the response variable, aka y's for the calculator. We put this one into L1. We put this one into L2. We called this H, and we called this C for caffeine, just to have a nice reference. Half-life. What does it mean to be a half-life? It means that is the time it takes for an amount to exponentially decay to half of what it started as, or half of its original amount. Okay, so in this case, we would look to see where it was about 40, which is right around 6 hours for the caffeine in this situation. Okay, in the next video, we're going to have example 3 and example 4 is we are going to have exponential growth and exponential decay, and we will compare these two models.